pumps is to provide flow for the hydraulic system. In this course, you will learn more about the three basic types of hydraulic pumps and understand the differences and similarities between these pumps, their fluid displacement capabilities, and their proper application in a hydraulic system.
Pumps are fluid power components which transform mechanical energy transmitted by a prime mover into fluid power energy. Gear pumps are compact, relatively inexpensive, and have few moving parts. External gear pumps consist of two gears, usually equal in size, that mesh with each other inside a housing. The driving gear is an extension of the drive shaft. As it rotates, it drives the second gear. As both gears rotate, fluid is drawn in through the inlet. This fluid is trapped between the housing and the rotating teeth of the gears, where it travels around the housing and is pushed through the outlet port. The pump creates flow and under pressure transfers energy from our input source, which is mechanical, to a fluid power actuator. The rotating portion of the pump, or rotor, is positioned off-center of the cam ring or housing. The rotor is connected to a prime mover by means of a shaft. As the rotor is turned, the vanes are thrown out by centrifugal force and contact the ring or housing, forming a positive seal. Fluid enters the pump and fills the large volume area formed by the offset rotor. As the vanes push the fluid around the cam, the volume decreases and the fluid is pushed out the outlet port. It is important before viewing this animation to understand the unbalanced vane pump. If you need to review it, go back and click on Unbalanced Vane Pumps. In the unbalanced vane pump, which has been previously illustrated, on half of the pumping mechanism, it is at less than atmospheric pressure. The other half is subjected to full system pressure. This results in side-loading the shaft, while under high pressure conditions. To compensate for this, the ring in a balanced vane pump is changed from circular to cam-shaped. With this arrangement, the two pressure quadrants oppose each other. Two ports take fluid in and two pump fluid out. The two inlet ports and the two outlet ports are connected inside the housing. Because they are on opposite sides of the housing, excessive force or pressure buildup on one side is canceled out by equal but opposite forces on the other side. With the forces acting on the shaft balanced, the shaft side load is eliminated. Flow is created in the same manner that you have seen illustrated in the unbalanced vane pump, the only difference being the two discharge and two suction cavities rather than one. It is notable that constant volume positive displacement vane pumps used in industrial systems are generally of the balanced design. In this learning lab, axial piston pumps convert rotary motion of an input shaft to an axial reciprocating motion of the pistons. This is accomplished by a swash plate that is either fixed or variable in its degree of angle. With the swash plate vertical, no displacement occurs because there is no reciprocating motion. As the swash plate increases in angle, the piston moves in and out of the barrel as it follows the angle of the swash plate. In actual design, the cylinder barrel is fitted with many pistons. During one half of the circle of rotation, the piston moves out of the cylinder barrel and generates an increasing volume. In the other half of the rotation, the piston moves into the cylinder barrel and generates a decreasing volume. This reciprocating motion draws fluid in and pumps it out.
There are two types of positive displacement hydraulic pumps: a fixed pump, which produces a fixed gallon per minute flow based on the RPM of the prime mover or electric motor, and a variable pump, which can vary its rate of gallons per minute while the input RPMs remain constant. Although displacement is typically measured in volume displaced per revolution, output is measured in gallons per minute or GPM. In this example, a motor turning at 1200 RPM is driving a fixed displacement gear pump, producing 5 gallons per minute flow. The GPM can be changed if the RPM of the motor changes. When a variable displacement pump is used in the system, the GPM can be varied in two ways. As with fixed displacement pumps, the GPM will be changed if the RPM of the motor is changed. The second way is to vary the displacement of the pump. For example, the displacement of an axial piston pump is determined by the distance the pistons are pulled in and pushed out of the cylinder barrel. Since the swash plate angle controls this distance in an axial piston pump, we need only to change the angle of the swash plate to alter the piston stroke and pump volume. Several means of varying the swash plate angle are used. They may include hand levers, mechanical stops, or more sophisticated hydraulically positioned devices. If the pump produces 5 gallons per minute flow with 1200 RPMs at maximum displacement, the GPM can be varied by moving the swash plate into the upright position or de-stroking the pump. This will vary flow from 5 to 0 gallons per minute. Before beginning this section, you should understand the difference between fixed and variable pumps. If you need to review the concept, return to the Pumps menu and click on Fixed versus Variable. Variable volume pumps can also be pressure compensated. A pressure compensated piston pump de-strokes or moves to zero output at a predetermined pressure. This is accomplished by hydraulically positioning the pumping chambers to zero output while maintaining compensator pressure at the outlet of the pump. In this example, we have used a pressure-compensated piston pump. It is helpful to understand the functionality of a piston pump. If you need to review this, return to the Pumps menu and go to the animation for the piston pump. As the pistons rotate around the shaft and follow the angle of the swash plate, they are pumping fluid out the outlet, which provides flow to move a component such as a cylinder. When the cylinder reaches the end of its stroke, pressure rises at the outlet of the pump as the fluid's flow path is blocked. This pressure forces the compensating spool up, allowing the pressurized fluid to energize the de-stroking piston and push against the swash plate, forcing it to a vertical position. With the swash plate vertical, the pump is now de-stroked and the pressure at the outlet port is maintained at a constant level. A very slight amount of flow is produced to maintain de-stroke pressure. This flow is bypassed into the case and carried back to the reservoir through the pump case drain outlet. Of the three,
this course on actuators will give you a good understanding of how actuators work in a hydraulic system. The actuator is the interface component that converts hydraulic horsepower back into mechanical horsepower. An actuator may either be a cylinder giving linear motion or a hydraulic motor giving rotating motion.
Cylinders are linear actuators. Their output force or motion is in a straight line. Their function is to convert hydraulic power into linear mechanical power. Their work applications may include pushing, pulling, tilting, and pressing. Cylinder type and design is based on specific applications. A ram is perhaps the most simple of the actuators. It has only one fluid chamber and exerts force in only one direction. It is used in applications where stability is needed on heavy loads. A single acting cylinder is pressurized on one end only. The opposite end is vented to the tank or atmosphere. They are designed so that the load or a device such as an internal spring retracts them. The double-acting cylinder is the most common cylinder used in industrial hydraulics. We can apply pressure to either port, giving power in both directions. These cylinders are also classified as differential cylinders because of their unequal exposed areas during extend and retract. The difference in effective area is caused by the area of the rod that reduces the piston area during retraction. Extension is slower than retraction because more fluid is required to fill the piston side of the cylinder. However, more force can be generated on extension because of greater effective area. On retraction, the same amount of pump flow will retract the cylinder faster because of the reduced volume caused by the rod. Less force, however, can be generated due to less effective area. A double rod cylinder is considered a non-differential type cylinder. The areas on both sides of the piston are equal, thus providing equal force in both directions. An application for such cylinders would be where it is advantageous to couple a load to both ends, or where equal speed is needed in both directions. The cylinder assembly is constructed of a steel cap end head, a steel barrel assembly, a rod end head, a rod bearing, a piston, and piston rod. Tie rods and nuts are used to hold the heads and barrel assembly together. Static seals keep the joint pressure tight. A rod wiper is provided to prevent foreign material from entering the bearing and seal area. Sealing a moving surface is provided by the rod seal, which prevents fluid from leaking past the rod, and by the piston seals, which prevent fluid from bypassing the piston. Fluid is routed to and from the cylinder through the rod end port and the cap end port. Hydraulic motors are classified as rotary actuators. Motors very closely resemble pumps in construction. However, instead of pushing on the fluid as the pump does, the fluid pushes on the internal surface area of the motor, developing torque. Resistance from the load is encountered, and pump flow provides a continuous rotating motion. Since both inlet and outlet ports may be pressurized, most hydraulic motors are externally drained. The four most common types of hydraulic motors are gear, vane, piston, and bent axis piston. Hydraulic motors are rated according to displacement and torque. The first consideration should be torque. Hydraulic motors are rated in foot or inch-pounds of torque per given psi, typically in pounds per 100 psi. Torque is equal to load times radius. Large displacement motors usually have a greater radius for the hydraulic fluid to push against. Therefore, they create more torque at a specific pressure. A hydraulic motor that is rated at 1 inch-pound force per 1 psi is rotating a winch with a radius of 4 inches. Our load is 500 pounds. The required torque is 2,000 inch-pounds. Based on the torque rating of our motor, our operating pressure would be 2,000 psi. The second consideration would be displacement. This is necessary to determine the amount of flow required to rotate the hydraulic motor at the required RPM.